we're going to start Chapter 5. So I think Chapter 5 is a lot easier, though we are going to introduce a new uh, math thing called the dot product, which if you're in Calc 3, you've seen dot products. I think in Calc 3, right? Dot products in Calc 3. Uh, they're pretty simple. I'll show you how to do them. In Chapter 5, we're dealing with energy. We'll deal with kinetic energy and potential energy. Kinetic energy is the energy of motion. I'll write this down in just a bit. And then potential energy is the energy for the potential of motion. And we'll deal with two types of potential energy, the elastic and the gravitational potential energy. So like having something in the gravitational field gives it the potential for motion, right, if I release it. And then also like a rubber band shooting across the room is potential energy. So if you have something that's elastic and you stretch it, then it contains potential energy. If you let it go, it moves. Then we'll also deal with work, and we'll see how we derive energy from the definition of work. And then how we calculate the work for a force that is variable over position, which we'll do with intervals. All right. But first, just a few things about energy. There are a lot of different kinds of energy. As I said, we'll discuss the energy associated with motion. That's kinetic energy, or that associated with the potential for motion. Which is potential energy. And then collectively, these two, kinetic and potential energy, we call mechanical energy. And this is in contrast to other types of energy, which we'll also deal with, electrical energy. Nuclear, we won't get to nuclear, but that's another type of energy apart from mechanical. And then maybe also thermal energy as well. Now, thermal energy you can describe classically as particles having kinetic energy. And I think in P-Chem, when you guys take P-Chem, physical chemistry, for those chemistry majors, one of your semesters in P-Chem is basically thermal physics. And you'll talk about how you describe a collection of gas particles by their kinetic energy and their potential energy, and how you can describe the thermal properties of a system. All right, so that's a whole semester in P-Chem is thermal physics. Basically, P-Chem is broken down into quantum physics for one semester and thermal physics for another semester, but all with sort of a, chemistry. Oh, P-Chem, I'm sorry. It's an abbreviation for physical chemistry. Here it's what, Chem, some of y'all are in it, aren't you? No, none of you are in it. It's Chem 3 something something. 5. Feels that way, doesn't it? Yeah. I think it's a good course, actually. All right, so let's talk about the dot product just a little bit. The dot product, it's also called the scalar product, is the product of the magnitude of one vector hold on. With a component of a second vector. And then the component of that second vector is in the same direction as the first vector. So basically, let's say we have these two vectors, A and B. We're going to take the magnitude of A, which is the length of that vector, and then multiply it times the magnitude of the component of this vector, which is bx. So basically, we're going to take two vectors and take the component of one that's in the same direction as the other, and then multiply those two. And that's what the dot product does. It just takes two vectors that are in the same direction, or if you have them one not in the same direction, it will take the component of that vector that's in the same direction and then multiply those two. All right? So mathematically, that's just what a dot product does. Is that what they teach you in Calc 3, sort of? Yeah. All right, well, physically, that's what it does. And when we're talking about, we're going to apply this in terms of work, we'll see why that's useful. So it takes the magnitude of one vector and multiplies it times the component of the other vector that's in the same direction as the first vector. You want two parallel vectors, basically. All right, so we define this. Right, if you go back to this picture that we had on the previous page, we have the vector A and then the vector B cosine theta, which is the vector that's in the same direction as A. And so that's going to be our definition of A dot B. A dot B is going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. And that takes that component of the second vector that's in the same direction as the first vector. Now, if they're in vector notation, and I'll do an example like this in just a bit, you just multiply out the components of the vector. So let's say, for example, I had two vectors. I had the vector A was equal to 2i plus 3j. And then I had the vector B, and it was equal to, say, 1i minus 4j. And I wanted to take the dot product of those. That would be A dot B. I just multiply them out like I would doing FOIL, for example. So I'd have 2i plus 3j dotted with the vector B, 1i minus 4j. So FOIL says first, so that's going to be 2 times I dot I plus the outer, which is 8 times I dot j. Oh yes, minus 8. Inner is 3 times j dot I, and outer is negative 12 times j dot j. Alright, so if I were to multiply those out like that with the FOIL method, first, outer, inner, last, you know what I mean when I say FOIL? Yeah, when you're multiplying two terms like that. Here, these I dot j, j dot I terms, they have certain values, and they're listed here. So I dot I, those are two vectors that are both in the x direction, and so it's going to be, by this definition of our dot product, it's going to be 1 times the cosine of 0, because I and I are in the same direction, so they, the cosine between them is 0. However, if I have I dot j right here, where the cosine is 90, then that angle is going to be 0, or excuse me, that dot product will be 0, because the cosine of 90 is 0. Similarly for I dot k, and j dot I, and k dot I, and j dot k. Anytime you have two vectors that are perpendicular, there is no component of that second vector that's in the same direction as the first vector, so the dot product will be what? It'll be 0, right. So anytime you have two perpendicular vectors, their dot product is 0. So anytime you have I dot j, j dot k, j dot I, those dot products are always going to be 0. Alright, so here I can get rid of some terms. This goes away, I dot j and j dot I, those go away because these dot products both equal 0. And it simplifies just to 2 I dot I, which is just equal to 1, minus 12 j dot j, which is just equal to 1. So that's equal to negative 10. And that would be the answer for the dot product. Oh, I had another example down here. Is it the same? It's very similar. Yeah, so, alright, you can do that one on your own if you like. Let's see. I don't have the answer here. Okay. We're going to do some examples where you have to do dot products. And on the exam, you'll very likely have to do a dot product with vectors that are written in vector notation. So make sure that you're up on that. We'll see some examples in just a bit. Y'all could do that on a test? Did y'all do dot products in Calc 3 this way, or did you do them some other method?
It was explained a little differently, but
Do you remember?
I find this is better. I don't know. He just told us to like in a book, it even says to just multiply the coefficients for each
Oh, okay.
part, and then to write it in vector form, you just
Oh, okay.
I, J, K.
Okay. All right.
It was explained a little more indirectly.
Okay. All right. Well, the reason we're using this is because we want to get one component of the vector in the same direction as the other, and that's we're trying to make two parallel vectors and then multiply their magnitudes. So if you want to think about it in terms of vectors, that's fine as well. All right. So this comes up when we're doing work. The reason we want to use a dot product is because of work. Work is done when a force is applied over some displacement. These are both vector quantities, right? So to calculate the work, we must multiply the magnitude of the force times the component of the displacement which is in the same direction as the force. So that is the definition then of a dot product. So we can say then that the work is going to be equal to F dot D, the force vector that is dotted with the displacement vector, and then this is also equal to the magnitude of F times the magnitude of D times the cosine of the angle theta. And that takes the force, the magnitude of the force, and multiplies it times the component of the displacement that's in the same direction as the force. Or if you want to think about it in a slightly different way, you can say it multiplies the magnitude of the displacement times the component of the force that's in the same direction as the displacement. That might be a better way for you to think about it, but it doesn't really matter because they're the same statements. All right, that is the magnitude of the displacement. It moves a certain distance times the component of the force that's in the same direction as the displacement. So say, for example, I had this object that's being moved by a force over a certain distance. So this would be like me pulling on this object, except instead I'm pulling up at an angle, right? So that's the force that I'm applying here. Now there's an X and there's a Y component to that force. There's an X component that moves along this direction, and then there's a Y component that moves in this direction. I was thinking, by the way, that, you know, at the grocery store, right, we push our grocery carts like this, but really that's not the best way to push your grocery cart, right? How should you move your grocery cart? Well, you should pull it like this. So I think that whenever we go to the grocery store, because you get less friction this way, right, you decrease the normal force. So next time y'all go to the grocery store, instead of pushing it like this, don't do that just because everybody else is doing it. You should do it like this. There's no reason why you shouldn't pull your grocery cart. Is there?
It's harder to turn.
Huh?
It's harder to turn.
It's hard enough. No, you should just try it out. You should try new things. Teach you. All right. So anyway, yeah, just tell everybody. Put a sign on your chest. All right. So if I want to know here the work that's being done, then my work in this case is going to be F times delta x, which is just my displacement, times the cosine of the angle between them. And that multiplies the component of the force times the displacement. And that gives me the work. Now, when F and D are parallel, that is, they're in the same direction, then this just becomes F times delta x. Because what is the cosine of the angle between them? Or what is the angle between those two, in this case, F and delta x? It's 0, right? And the cosine of 0 is just equal to 1. So sometimes when our force and our displacement are in the same direction, I'll just write it like that, and you might as well. But it's always assumed that I have this cosine theta term, and in this case it's the cosine of 0 degrees, and the cosine of 0 degrees is just equal to 1. So we might just write that as force times displacement to give our work. But that's assuming then that that cosine theta term is equal to 0, or is equal to 1 rather. Let's see, did I do? Yeah. All right. The units for work is the joule. Actually, sometimes you'll see the units for work as the Newton meter, because a joule is actually equal to a Newton times a meter. Remember, our work is equal to force times displacement. Force is in newtons, displacement is in meters, and so the units then would be in Newton meters. Sometimes you'll see work listed in Newton meters versus joules. Joules is also going to be the unit that we use for energy, but as we'll see, work and energy are closely related. That when you do work on an object, you increase its energy. Also, you might begin to see on some of the tests the basic SI units for this. So you can break these units down into more basic SI units. Remember, in the MKS system, we use what, and what for our basic SI units. Meters, right? Meters, kilograms, and seconds. That's the MKS versus the CGS, where you use centimeters, grams, and seconds. So in the MKS system, we would break this further down into, let's say, newtons is kilograms, meters per second squared, and then I have another meters, so that's going to be 1 kilogram meter squared per second squared. So you might begin to see some questions like that, just multiple choice questions. What is the basic SI units for work, or energy, or momentum, or whatever? And you always want to return to the equation and see what are the units of the constituents of that equation, and then just, you can find the basic SI units from there. You okay with that? We're going to begin to build units upon units as we develop different equations. Okay. Let's see, if there is no displacement in the direction of the force, then there is no work done by the force. So that would be like if my displacement is in this direction, but my force is in this direction. Now, obviously, that force is not causing that displacement. Then the work done by this is equal to 0. And if we return back to our dot product, we'll see that because what's the angle between F and D in this case?
90.
It's 90 degrees, and the cosine of 90 is equal to 0. Right, so that works out in our dot product. So if you imagine that you have this bucket of water, right? You ever seen Jack Candy? Or y'all know Jack Candy? Deep thoughts like Jack Candy. You have no idea who that is? It was like on Saturday Night Live, back before Saturday Night Live got trashy, like it is today. Where they'd come up with deep thoughts. Anyway, Jack Candy had this deep thought. It's like they had this soothing music playing, and he had this soothing voice saying this thing, and he said, what was it? Sometimes I wish that I had 2 sacks, and I would carry these sacks around all day. And anytime somebody would ask me to do something, I'd say, sorry, got these sacks. Deep thought. Anyway, so imagine that you're just carrying these buckets of water around, and I'm applying a force now in the y direction, but I'm moving at a constant speed in the x direction. Now in that case, I'm not doing any work on the object because my force that I'm exerting to hold it up is up, but my displacement is in the x direction. All right, so here I'm doing no work because my force is up and my displacement is to the right, and so work is equal to FD cosine theta. But here my theta is equal to 90 degrees, and so the cosine of theta is equal to 0. All right, sometimes we'll have dissipative forces that will also do work, like friction, for example, but they generally do negative work because the displacement and the force are in opposite directions. So let's say that I have an object and it has a couple forces acting on it. It has one force in this direction and it has a frictional force in this direction. All right, but let's say that my displacement, D, is to the right. Now notice here that my displacement, which is to the right, is opposite the direction of the kinetic frictional force. So then I would say that the work done by the kinetic frictional force is negative. And in our dot product, it would work out like this. I would say that the work is equal to Fk times d times the cosine of what? What's the angle between the kinetic frictional force and the displacement?
0.
No, it's not 0. These are anti-parallel vectors, and so they're 180, right? And that's where that negative comes in, because the cosine of 180 is equal to negative 1. All right, so the work then done by this is going to be a negative work. The work done by that force is negative. So if I have a force that's opposite the direction of the motion, it's going to produce a negative work. Now, is work a scalar or a vector quantity? I haven't said this, but what do you think it is?
Wouldn't it be a vector because the direction of the force you're using determines whether it's positive or negative?
Okay. No. Good shot. Is it a vector or scalar quantity? It is a scalar. Remember, the dot product is also called the what product? The scalar product, right? So that's clear. But I'm multiplying two vectors, but the result of this is actually a scalar quantity, right? Now, then, if that's the case, why then would the work be negative? Because usually, up till now, we've used negatives to denote a direction, right, Courtney? And that's why you think it's a vector. But up to now, we've used negatives to denote a direction. So why would the work be negative?
It's just a notation.
But what does the notation mean? You're right, it is just a notation, but what does it physically mean to have a negative work? Remember, work is very closely related to energy. So if I do work on an object, we'll get into this next time. If I do work on an object, I give the object energy. What does it mean to have a negative work?
Take energy.
Object's giving you energy?
No, Courtney, you're right. You're sort of right, but you're actually taking away energy from the object. So anytime you have a frictional force, if it opposes the direction of motion, it's going to cause the object to do what? To lose energy or slow down, right? So a negative here, when we're talking about work, means that you're taking away energy. So work is a scalar quantity, and a negative work means that you're taking away energy. Let me write that. It's a pretty important point. Work is a scalar quantity. Negative work means you're taking away energy. We'll see that in some problems next time. All right, let's look at this next question. We're just going to do part A of this next question, just where you do the dot product of the two vectors. Okay, so here, I just want you to do part A. We haven't gotten to the other definitions yet here, so let's just do part A. I have a force vector, and then I give you the initial and final displacement, and I want to know how much work has been done by the force. So go ahead and do part A. We'll come back later and do parts B, C, and D. I think we can go ahead and do part C and D. And I'm going to go ahead and tell you what power is. We're not going to come to this till the end. But power, P, we'll call it, is just the work done over the amount of time. We'll sort of redefine it a little bit differently next time. But once you find the work, you can find the power just by dividing it by the amount of time. And then go ahead and do C and D as well. Anybody have a work yet? No? Alright, does anybody have A? What do you got? 25 is right. Yeah, so you're taking the dot product, F dot D. That's going to be 3I plus 4J. Dotted with the difference in these two. So that's 3.25 minus 0.25, which is 3I. 4.5 minus 0.5, that's final minus initial position, plus 4J. And then you dot this. I'm not going to do the whole FOIL, right, because I really just need to multiply like terms. So that's 3 times 3, which is 9, plus 4 times 4, which is 16. So that's 25 joules or 25 Newton meters. All right, so that's the work that's being done. What then is the power? 12.5, right. So the power is just 25 joules over the time, which is 2 seconds, which is 12.5 or 13. What's the unit for power? What? It's watt, yeah. Yeah, what's the unit for power? What's the unit for power? Y'all don't get that, did you? You should never have to explain your funds. Like, everybody should get them right off. Okay, and then what is the mass of the particle? I have an idea. I have a hint here that the x displacement is 1/2 ax t squared. With that, how would I find the mass of the particle? How is A related to the mass? Right, so I know that F equals ma, so A equals F over m, right? So I can say then for part C that x is equal to 1/2 F over m, that's Fx, right, times t squared. What does that give me for m? You got it, Courtney? No? We're looking at our x displacement, which is 3.25 minus 0.25, or 3 meters. What is Fx? What's that? 5? No, the x displacement, the initial position is 0.25, and the final x position is 3.25. And so the difference in those 3.25 minus 0.25 is
you just found the distance at x, not to the whole.
the x displacement.
X.
Mm-hmm. All right, so that's going to be 3 newtons over their mass, and then our time is 2 seconds squared. And then we can solve for m here. Let's see, that cancels there. 1 is equal to 2 over m. So m equals 2 kilograms. We'll skip D for now. We'll come back to part D after we get into energy, and we'll find the magnitude of the final velocity later. All right? Why don't we stop there? Don't worry, we're going to work through a lot more problems similar to this in the class, and we'll deal with this a little bit later. But why don't we stop there? And I'm going to hand back your exam and just give you some time to look over it. I'm going to want to keep your exam, but you can look over it now. And if you want to take some time to sort of talk to one another and sort of see what you can do, you can do that. I'm just going to go in my office, and y'all can work for the remainder of the class on the problems. Is that clear what I mean? Like, you can talk to one another about your exams while you're in here, and just take a look at your exams. And I'm going to walk you back, please. That